Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to talk on the module Sensors and Transducers from the paper Electronics. So students, after completing this module, you will be able to learn transducers and sensors, sensor properties, electrical transducer, the various characteristics of transducers. We will discuss about the active and passive transducers, signal conditioning, that is DC and AC, position transducer. We will discuss about the strain measurement and different types of resistance strain gauges. So students, let us start with the basic introduction about the module. A transistor is a device which converts one form of energy into the other. So examples of common transducers includes the following. A microphone converts the sound into electrical impulses, and a loudspeaker converts electrical impulses into the sound. That is sound energy to electrical energy and vice versa. So a solar cell converts light into electricity and a thermocouple converts thermal energy into electrical energy. An incandescent light bulb produces light by passing a current through a filament. Thus, a light bulb is a transducer for converting the electrical energy into the optical energy. An electric motor is a transducer for the conversion of electricity into the mechanical energy or motion. Whereas a sensor is a device that receives and responds to a signal. This signal must be produced by some types of energy such as heat, light, motion, or chemical reaction. Once a sensor detects one or more of these signals at the input, it converts it into an analog or digital representation of the input signal. Based on this explanation of the sensor, we should see that they are used in all aspects of life to detect and or measure many different conditions. Human beings are equipped with 5 different types of sensors. Eyes detect light energy, ears detect acoustic energy, a tongue and a nose detect certain chemicals, and skin detects pressure and temperature. Eyes, ears, tongue, nose, and skin receives these signals, then send messages to the brain, which outputs a response. Transducers. So students, let us discuss about the transducers. Transducer is a device that receives energy from one system and transmits it to the another in a different form. It is a device which is capable of being actuated by an energizing input from one or more transmission media, and in turn generating a related signal to one or more transmission systems. Let us now discuss about the principle of transducers. Transducers provide a usable output in response to a specified input measurement, which may be physical or mechanical quantity, property or conditions, and energy transmitted may be electrical, mechanical, and acoustical. The applications of transducers are: they can be mechanical, electrical, optical, acoustic, magnetic, thermal, nuclear, chemical, or any of the combinations. The examples are: electric motor converts electrical to mechanical. Loudspeaker converts electrical signal to variable magnetic or acoustic. Loudspeakers can act as microphone also when connected to the amplifier input, that is acoustical sensors. Sensors. Sensors are the devices which are capable of detecting the change. Their use is to understand and interpret the ambient. Now, detection, it can be physical, that is heat, pressure, humidity, light, sound. Second, chemical, gas, liquid, solid, organics or inorganics. Lastly, biological, DNA, protein. Now, the importance of sensors. These are the devices that can extend the human physical senses of sight, hearing, taste, smell, touch, that is pressure, temperature, and chemicals. Environmental sensors as an extension of human senses the same phenomena as a human sensor, but they are 24 hours a day, 365 days a year. Measurements are more precise, sensitive, and selective. Measurements are reproducible. Transducers and sensors. Let us compare the two. Transducers are the devices which are an essential element of sensors. So, a sensor is a sophisticated transducer in the sense that it contains some signal conditioning circuits capable of amplifying and refining the weak and raw signals available at the output of the transducer. Some of the signal conditioning circuits are amplifier, filters, analog to digital converters. Let us now discuss about the sensor properties. The first is the response time. The response time is the time taken by the sensor to approach its true output when subjected to a step input. It is more usual to quote a sensor as having a flat response between specified limits of frequency, that is frequency response, and it indicates that if sensor is subjected to sinusoidal input of constant amplitude, output will faithfully reproduce a signal proportional to the input as shown in this figure. Let us now discuss about the recovery time, which is shown in the circled portion in this figure. It is basically the amount of time for a sensor to reset its initial state so that it can be used again. Next is reproducibility. It is the ability of the sensor to have the same output response given the same amount of measurement. Aging. After repeated use over a long period of time, the sensor eventually degrades. The time it takes to degrade describes how the sensor ages. So this is shown in this figure, which shows at one point of time the response is a flat, and after certain time elapses, the response versus time graph changes. Another property is the stability. This is described how well behaved is the sensor response. That is, in this figure, we can see a stable sensor whose response is a very stable and a very flat response is there. And in the case of unstable, we have the response as a very noisy graph. The next one is the response. It is nothing but the ratio of the response above background divided by the background. That is, X is equal to the S, the response is equal to C is equal to the modulus of XR minus XA divided by XA. So the response is the change in the output of the sensor per unit change in the parameter being measured. So the factor may be constant over the range of the sensor, that is linear, or it may vary non-linearly. So resolution is very important parameter, which is nothing but the smallest amount of increase in the measurand to cause an increase in the output, that is here it is M1. So this shows the response versus the measurand graph. Next one is a dynamic range. It is the range of the measurand values that the sensor respond to, that is M2 to M1. Span or input full scale, FS. Dynamic range of stimuli that may be converted by the sensor. It represents highest possible input which can be applied to the sensor without causing unacceptably large inaccuracy. Next is full scale output, FS, is the difference between the electrical output signals obtained with the maximum input stimulus and lowest input stimulus applied. Includes all deviations from ideal transfer function. Next one is the accuracy. Now, inaccuracy is the highest deviation of a value represented by a sensor from the ideal value. Next, and linearity. It is the most convenient sensor, which is one with a linear transfer function. Output is proportional to the input over entire range, so the slope of the output or the input detection is a straight line. Next one is the calibration. If a meaningful sensing has to be made, it is necessary to measure the sensor output in response to an accurately known input. This process is known as calibration, and the device that produces the input are described as the calibration standards. Next, we have the range. Every sensor is designed to work over a specified range. Design ranges, they are usually fixed, and if exceeded, results in a permanent damage or destruction of the sensor. Let us now discuss about the electrical transducer. An electrical transducer is a sensing device by which the physical, mechanical, or optical quantity to be measured is transformed directly by a suitable mechanism into an electrical voltage or current proportional to the input measurand. So students, electrical transducer is always preferred because of the following reasons. The signal can be conditioned, that is modified, amplified, modulated, etc. as desired. Second one, the output can be indicated and recorded remotely at a distance from the sensing medium. Thirdly, the electrical or electronic system can be controlled with a very small power level. Lastly, the electrical output can be easily used, transmitted, and processed for the purpose of measurement. So, electrical transducers are of two types. First is the active transducer, which is nothing but a self-generating device. Second is a passive transducer, that is, which do not generate any energy. Let us now discuss about the characteristics of transducers. First is the operation range. It should be chosen to maintain the range requirements and good resolution. Next is the sensitivity, which is chosen to allow the sufficient output. Frequency response and resonant frequency, the flat over the entire desired range. Next is environment compatibility, that is temperature range, corrosive fluids, pressure, shocks interaction, size and mounting restrictions. Minimum sensitivity to expected stimulus other than the measurement. Accuracy, repeatability and calibration errors, as well as the errors expected due to the sensitivity to other stimuli. Usage and ruggedness. Ruggedness, both of mechanical and electrical intensities versus size and weight. Electrical parameters, length and the type of cable required, signal to noise ratio when combined with amplifiers, and frequency response limitations. So there are two types of transducers, active and passive transducers. Active transducer, which generates an electrical signal in response to the physical parameter and does not require any external power source for its operation. They operate under energy conversion principle and generates an equivalent output signal. So the examples are piezoelectric sensors, that is generation of charge corresponding to the pressure, photovoltaic cells, generation of voltage in response to illumination, etc. Next is a passive transducer. They operate under energy controlling principles, which makes it necessary to use an external electrical source with them. They depend upon the change in electrical parameter R, L, and C. Typical examples are strain gauges, that is, the resistance changes in response to the pressure, thermistor, resistance changes in response to the temperature variations, etc. Signal conditioning. Signal conditioning refers to the operations performed on the signals to convert them to form suitable for interfacing with other elements in the process control loop. The two categories of signal conditioning process are: first is a linear process, that is amplification, attenuation, integration, differentiation, addition, and subtraction. And in the case of non-linear process, we have modulation, demodulation, sampling, filtering, clipping, and clamping, squaring, linearizing, or multiplication by another function. Also, signal conditioning can be of two types depending upon the type of input signal. First is DC signal conditioning, second is AC signal conditioning. So let us now discuss these two types of signal conditioning. DC signal conditioning. So this figure shows the block diagram for a DC signal conditioning. Now here the transducer constitutes one or more arm of the Wheatstone's bridge, which is excited by the DC source. The bridge can be balanced by using a potentiometer and can also be calibrated to indicate the unbalanced condition. The output of the calibration and zeroing network is connected to the DC amplifier for amplification, followed by low pass filters. The low pass filters are used to eliminate the high frequency components or noise from the data signals. Let us now discuss about the AC signal conditioning. So this shows the block diagram of the AC signal conditioning. Now here the transducer used are of the variable resistance or variable inductance type between carrier frequencies 50 kHz and 200 kHz. The output of the transducer is applied to the bridge circuit, whose output is an amplitude modulated carrier signal which is amplified by an AC amplifier. The amplified modulated output is then applied to a phase sensitive demodulator carrier signal. So active filters can be used to prevent the overloading of the amplifier. DC systems used for common resistance transducers, potentiometer, resistance strain gauges, etc. AC systems are used for variable reactance transducers and for the systems where signals have to be transmitted via long cables to connect the transducers to a signal conditioning equipment. Let us now discuss a type of transducer, that is a position transducer. Transducers measures the position or the displacement by exhibiting a resistive, inductive, capacitive, or piezoelectric change as a function of the change in position. Let us now discuss about the resistive position transducer. The change in position can be monitored by measuring the change in resistance of the sensing element. So in this figure, this type of transducer uses a resistive element with a sliding contact or a wiper linked to the object being monitored or measured. The resistance between the slider and one end of the resistance element depends upon the position of the object. So we can reduce the above circuit or the above schematic of the position transducer into an equivalent circuit. That is, here the output voltage is dependent on the wiper position and is therefore a function of shaft position, that is V0 by Vt equal to R2 by R1 plus R2. This shows that the output voltage is proportional to R2, that is the position of the wiper of the potentiometer. So if the resistance of the transducer is distributed uniformly along the length of the travel of the wiper, the resistance is perfectly linear. Let us now discuss how to measure the strain. When a force is applied to a solid at rest, it gets mechanically deformed. Tensile force leads to the increase in the length of the solid, whereas compressive force decreases the length of the solid. So the longitudinal strain is defined as epsilon equal to delta L by L, where delta L represents the change in the length to its original strength and L is the original length. Let us now discuss about the types of resistance strain gauge. First type is a wire strain gauge. Now there are two types of wire strain gauge: unbonded resistance wire strain gauge. Second one is a bonded resistance wire strain gauge. A second one is a foil strain gauge type of strain gauge. And lastly, we have the semiconductor strain gauge. Students, let us now discuss about the unbonded wire strain gauge. It consists of a wire stretched between the 2 points in an insulating medium such as air, as shown in this figure. The wires are kept under tension so that there is no sag and no free vibration. They are usually connected in a bridge circuit and bridge is balanced with no load applied. Second one is a bonded wire strain gauge. So here we have a fine wire element which is looped back and forth on a carrier or mounting plate which is cemented on it, undergoing stress. So the spreading of the wire permits uniform distribution of stress, and the carrier is then bonded to the member being studded, permitting a good transfer of strain from the carrier to the wire. This is clearly shown in this figure. Strain gauge in bridge measurement. So let us now discuss about it. Strain gauge used in the bridge arrangement, in which gauge forms the one arm of the bridge as shown in this figure. Only one gauge is active element, producing an output proportional to the strain. Other gauge is simply used for balancing. And as shown in this figure, there is a one dummy gauge which is used to remove any error due to temperature variation. Since only one gauge responds to the strain causes bridge unbalance, just as in the case of a single gauge. The second one is a foil strain gauge. Here the strain is sensed with the help of a metal or alloys foil. They have much greater dissipation capacity than the wire wound gauges on account of their larger surface area for the same volume. So this type of gauge is shown in this figure, and they can be fabricated on a large scale and in any shape where foil can be etched on a carrier. Edged foil gauge construction consists of first bonding a layer of strain sensitive material to a thin sheet of paper or bakelite. The portion of the wire is covered with the appropriate masking material, and the portion which is not masked is removed, leaving the desired grid structure. The third type of strain gauge is a semiconductor strain gauge, which is shown in this figure. Now here their action depends upon the piezoresistive effect, that is a change in the value of the resistance due to the change in the resistivity. Semiconductor materials such as germanium and silicon are used as the resistive materials. It consists of strain material and leads that are placed in a protective box. Gold leads are used for making contacts. So let us now study the advantages and disadvantages. They have a very high gauge factor and allows the measurement of very small strain. Hysteresis characteristics of semiconductor strain gauges are excellent, and they are very small in size. But they comes with disadvantages also. They are sensitive to the changes in temperature. Linearity is poor, and they are much more expensive. So students, let us now summarize what we have learnt in this module. Firstly, we discussed about the temperature and sensors, that is how they are different. The sensors properties were discussed. Thirdly, the electrical transducer was discussed in detail. Now, different characteristics of transducer, that is what characteristics they should have, were discussed in detail. A comparison between an active and passive transducers was made in this module. Next, we discussed about the signal conditioning, that is for the DC signals and for the AC signals. Next, we discussed about a very important transducer, that is a position transducer. Lastly, the strain measurement and different types of resistance strain gauges which are used to measure the strain were discussed in detail. Thank you.